So, Sapna, let's begin.
Okay, so good evening, everyone, or good morning, or good afternoon, depending upon from where you are who are joining us today. On behalf of Indian Association of Physics Teacher, I am delighted to extend a warm welcome to each one of you to our online program, a lecture series on physics education research. Through this platform, we aim to foster a vibrant community of practice that encourages the exchange of ideas, collaboration, and continuous learning. Today is the 11th lecture of this series, and it's both an honor and a privilege for us to welcome our distinguished guest, Professor Carl Wieman, a Nobel laureate in physics, whose contributions to the field of physics have not only expanded the frontiers of our understanding, but have also brightened the path for future explorations. Professor Wyman's work on the production of the first true Bose-Einstein condensate has opened new avenues in the study of quantum mechanics and matter itself. Beyond his remarkable achievement in research, Professor Wieman has devoted a significant part of his career to science education and especially to physics education. His life's work inspires us a lot. We are immensely grateful to you, sir, and eagerly anticipate the insights and inspirations you will share with us today. I also extend a warm and sincere welcome to the President of Indian Association of Physics Teachers, Professor P.K. Ahluwalia, all the senior professors present here, and the Secretary of IIPT, Ma'am Rekha Ghorpade. I also welcome all the participants who have joined us today. Let's enjoy the talk of Professor Carl Wieman. And for the further proceedings, I hand over the mic to Professor P.K. Ahluwalia.
Thank you, Sapna. Thank you very much. And good morning, Carl, and good evening to everyone here in India. We are very happy that you are on a virtual visit to India. Welcome you to this visit. In fact, I take this opportunity to welcome you on behalf of Indian Association of Physics Teachers. And I am delighted to extend our greetings to you on this very special occasion for us. Dear participants, Professor Carl is a well-known person, and in his Nobel Prize, there is an Indian connection also sitting there, because he discovered that Bose-Einstein condensate. So, sir, this is also a matter of pride for us that you discovered that for which people were waiting for almost 100 years. Thank you very much for that also. But there is something very special which is there, and that is what is very also interesting for this community of physics teachers from India. And that is your love for bringing reforms in the way physics education actually is being transmitted in the world. We know your monumental work for physics education in the form of physics education technology interactive simulations. Sir, let me tell you that during COVID, we were a practitioner of this physics education technology simulations for reaching to our students in schools and colleges. So thank you for creating a resource which became so valuable for us during a very, very tough time through which world passed. Dear participants, Professor Wieman is a practitioner of physics education. And sir, when about 15 years back, I read one of your articles, Are we teaching science scientifically? And in today's talk also, I am finding an echo of that thought itself, which you are carrying with you, and you are very passionate about it. Also, I would like to tell you, sir, that India at present is passing through a very interesting formulation of its education. We launched in 2020 our national education policy, and we are now at an implementation stage. And we are very ambitious in that education policy and bring those elements which technology can actually help us in bringing. And we very much uh, look forward to your uh, talk today so that we can really take that agenda forward with a lot of optimism and futuristic ideas which our country wants to get to our students in schools, colleges, and universities. So with these words, I once again welcome you, and may I request you to please deliver your lecture. Thank you very much.
Okay, well, thank you. Thank you for such a nice introduction, and it's a pleasure to speak to all of you, keeping you up late at night to hear me. I hope it'll be worth it. If I have one short request is that if you could you please mute your speakers? Sometimes it can be distracting in the middle of the talk if there's noise coming in. So let me share my screen here. So yeah, I'm going to be talking to you about taking a scientific approach to physics education. And so what I'll start is just a general introduction about research on how the brain learns complex thinking. And then I'll talk about how these ideas have been applied in university classrooms and measuring results. This is really done by many people, but some in my own research group. And then I'll focus in tighter, giving some sort of detailed findings from this classroom research in physics on what works to improve learning and why. And these are sort of more things you can use in your own teaching. Now, before I get into that, though, I want to just give you a little bit of background on how I got involved in this education work and sort of my perspective on the work. And it really started not with the classroom teaching. It was really my working with my graduate students in my atomic physics research lab. And I saw this repeated pattern that these students would come in to work in my research lab as PhD students after many years of great success in their math and physics classes, but they really didn't seem to know how to do physics when they were, put in the research environment. And but there was clearly not anything fundamentally wrong with them, because after just a few years working in my research group, they had turned into expert physicists. And so when I saw this originally, I thought it was just a peculiarity of a few people, but then I saw it happening over and over again, and I decided there was a real fundamental question here. And so I treated this as a science question. And I really started looking hard at what the research was on how people learn, particularly how they learn physics, to try and make sense of this. And there was, this was 35 years ago, but there was at that point a respectable amount of research in both these areas, and it explained the puzzle so I could understand why this was happening. It also made me realize there were much more effective ways to teach than what was being used in most of our classrooms. But then it also got me interested in this field and got me started in doing research on physics learning, doing experiments, collecting data, and abstracting basic principles from that. But all of this time, my work is the sort of central focus of my interest has been expertise. What I mean is that's how one thinks like a good scientist, thinking like a good physicist or engineer, and what is that way of thinking, and how do we develop it? Now, over the past couple of decades, there's actually been major advances in these in actually understanding the learning and teaching of this kind of complex thinking like a scientist. And it comes from there's research from sort of three complementary areas. There's the brain research, which I won't talk much about today. And then the things I'll focus on is the work in both cognitive psychology, where they study the basic processes, often in labs, of how people think and learn. And then the work from people like myself, where faculty, physicists, biologists, etc., are doing experiments in university classrooms, doing experiments, collecting data. Now, a lot of times people, the data is really almost all from universities, and so people wonder how general this is. And I'll say that without getting into details, the ideas certainly at least apply to the level of high school, and possibly somewhat younger than that. So what is all this research shown us? Well, at the most basic level, it's really had us rethink how the learning process happens. Now, the old and still widely pervasive current model of this at the university level, it's really that these student brains come into our classrooms and they vary in different ways, and we immerse them in knowledge. And then that knowledge soaks in to different amounts depending on what the brain was like. And so with this model of learning, then the focus is on selecting the best brains, giving lots of tests and so on to sort students, and then thinking about what goes into this knowledge soup, what's in the curriculum, which topics to cover and when. Now, as I say, this is a very pervasive model at present, but it's just plain wrong. The research gives us quite a different view of this. And what research says is that these brains, particularly at the university level, don't start out all that different. But what's important is the brains are actually changeable, that they transform through the educational process. Actually, the neurons are rewired, hooked up in different ways as a result of intense thinking that's going on in their education. And this rewired brain has improved capabilities. And so the learning process is really needs to be thought of as one of changing the capabilities of the brain. And we can even see this with modern brain imaging. I'm showing here a functional MRI images of the brains of two people who are interpreting medical x-rays. And on the right is the brain of a medical student who's just learning this. On the left is an expert radiologist who's very experienced at this. And you can see their brains are actually being activated in very different ways. And this is as the change in the brains come about through this educational process. So what the research is telling us is that learning is really about finding, enhancing the right kind of neuron connections. And the brain is actually learning the thinking that it practices doing. And so it's very analogous to muscle development, that if you want to make a muscle bigger and stronger, you have to exercise that muscle strenuously over a long period of time, and it gets better. And that's what we see, very similar to what happens with the brain. But so the intensity and type of exercise is really critical. And to a large extent, that's a lot of what the physics education research is now looking at is how to make it more intense and the type of mental practice or mental exercise more effective to help the brain better develop these new skills. So that's sort of the big introduction. Now I'm going to talk about some research on what applying these ideas in university classrooms and the kind of results that we can measure in those. So the first example I want to give of this is it's in a very large introductory physics class for all the people planning to be engineers. And the class was large enough we could have two sections that we'd identified with 270 students each, but we'd identified that the student populations were essentially identical in their background and knowledge and so on. And then these two sections were taught in two different ways. So the one way, the control section, it was taught by a highly experienced professor who had good student ratings, but taught in this fairly essentially a standard lecture approach. And the experimental section was taught by someone with a fairly new PhD, but they'd been trained in the program I ran in these principles and methods of research-based teaching. And these two instructors then agreed to cover the same material and the same amount of class time. And then they jointly prepared a test on this material that they would give to the students right after this interval of classes covering this topics were covered. So I assume you know what the standard lecture teaching was like. The professors, they're talking and students are listening, taking notes. The experimental class, what it was like was the students first had a short pre-class reading assignment to sort of give them basic facts and terminology without needing to spend class time on that. And then class would start with questions for like this one, where you have a circuit with a battery and light bulbs here. And the question is, what's going to happen to the brightness of bulb 2 when you close that switch? And the students are given 4 choices to select from. And each student then has to answer this question. And so you're collecting data on really all of the students. They do this with, at the time this was done with a special device called a clicker. Nowadays, people are doing the same thing, just using mobile phones. But basically each student then answers, and the instructor's computer records who they were and what answer they chose. Now, But after they've all made their choice, they're not told what the answer is. Instead, they're told to talk with their neighbors about what the answer is and why, and re-vote on after this discussion. Now, while they're talking, the instructor isn't just sitting waiting for them to finish. The instructor is actually circulating up and down the aisles, listening in on these conversations to get a little snapshot of how the students are thinking, what aspects of their thinking are what you want, like a physicist, and what aren't, and what are areas of confusion. So after that vote, then there's demonstration to show the result of what happened. But then the instructor has a follow-up summary where they give feedback on what models and thinking of the students were correct and which were incorrect and why. And I emphasize that particular one because one of the things cognitive psychologists have shown us is that the main learning process is not when you do things right, it's when you do things wrong and you're helped to understand why your thinking was wrong and how it needs to change. Now, this wasn't all done just with simple multiple choice questions like this. For more mathematical topics, the students would have to write out solutions on worksheets, but again, done in consultation with fellow students, nearby neighbors in the class. So if you think about what kind of mental exercise these students are getting, they're practicing thinking like physicists. They're having to decide on a conceptual model for electricity, and then they have to think about how it's going to apply in this particular situation, and then they test their predictions and test their conceptual model and their reasoning, and they're critiquing their own reasoning in this process as well as that of their fellow students in the discussion. And while they're doing this practice thinking, they're also getting feedback on it, and they're getting it from other students in the discussion. They're getting it by comparing their prediction with the demonstration of what happens, and they're getting it from the informed instructor who's informed by listening to the conversations and seeing what the class vote was. So this is really the two critical elements of effective learning, is having students practicing the thinking you want them to learn with feedback to help them improve. Now, so remember, this was part of an experiment, so they're both given this surprise quiz in both sections. And these are the results of that quiz. You can see the histogram of the number of students with their scores here, and with the experimental section in blue and the standard lecture in red. And you can see there's a profound difference between the two. Now, in fact, on this particular test, random guessing would give a person about 3. And so you, especially when you appreciate that the amount of learning is sort of how far above 3 you are, you can see how first the learning from the lecture is tiny, and we see this in many other studies as well. But also the second point I want to emphasize is that the entire distribution has moved up. So this shows that this way of teaching isn't more effective just for the weaker students or just for the stronger students. It's really clearly better for the entire population of students. Now, most of the research in physics education has been done on these introductory courses, but a number of people, and particularly my own group, have been looking at more advanced physics courses, and we've seen that applying the same basic principles, the details of implementation have to be adjusted, but the same basic principles of practicing the thinking and getting feedback on it seem to work also at more advanced levels. And so we've shown how transforming a course like this gives a standard deviation improvement in student performance compared to when they had lectures on the material. And in fact, we now at Stanford, virtually all the standard undergraduate physics courses have been transformed to have this sort of research-based teaching, sometimes called active learning, where students are busy working together, and in advanced classes, almost always using worksheets, making decisions, calculating, working in small groups while the instructor is monitoring what's happening. And in fact, we even have examples of this for advanced graduate courses being successful. Now, just to get into a little more detail about how these courses work, that we've seen this basic structure be successful for almost every subject and level of course. And the structure is that the students have to do some sort of modest preparation ahead of class, and then the instructor will introduce the tasks for the day, and then the students will work in these small group activities for typically 10 or 15 minutes, working through answering questions and discussing, while the instructor's circulating around, listening, seeing how they're monitoring how they're doing, maybe answering some individual questions. And then after they've worked on this for 10 or 15 minutes, get to sort of a reasonable stopping point, the instructor will then pull the whole class together to give them feedback on how they're doing, sort of try and bring everybody up to a similar level. And then the students will then go back and go back to working through the activities in their small groups. And that process then just continues through and as long as the class goes. And the essential features in all of these are that the students are busy thinking, they're getting mental exercise, practicing the expert reasoning you want them to acquire, and the instructor is much more knowledgeable. They're monitoring their thinking and seeing what the students are doing and struggling with, and so they can give much more effective feedback. So just to wrap up this part of the talk, those are just some examples of things people are doing, but there's actually, I tabulated this, something close to 1,000 research studies across many different fields of science and engineering at the university level that are comparing this kind of traditional lecture with this research-based teaching. And the research-based teaching consistently shows greater learning and lower failure and dropout rates.
Oh,
So now I want to raise another question though, which is that, we saw results like this in many classes, but once I was started at Stanford and seeing this, I started wondering, this is better for the class as a whole, but we still have a lot of these students down here who are not doing so well. And so how can we compress this distribution to make all students more successful? And I got particularly interested in this once I started at Stanford about 10 years ago, because Stanford, is a very selective institution. And so you'd expect all the students to be successful, and many weren't in their introductory physics. And so we started studying this quite a lot and found that just changing the teaching methods wasn't enough. It shifted the distribution, but didn't compress it. And we tried to figure out what other factors were important here. And we looked at got lots of data and did lots of fancy statistical analysis. But we found that what it really seemed to matter was a tremendously important factor was their prior preparation in physics before they got to the university. And this was a very strong predictor of how they would do in their introductory physics course. and we collaborated with people at other universities, and we saw the same thing, same dependence happen there. And so what we realized was the case is that instructors, I think without really thinking about it, were really optimizing the coverage and pace of these courses for the sort of top third most educationally privileged, best prepared students. And as a result, they were really sacrificing the ones who didn't have the privilege of as good a physics education in high school. And so we decided, this is really a problem with the teaching, not with the students. And so we felt that it just needs to think harder about matching the curriculum with the students and the full range of backgrounds they have, and that many more of them can succeed. And so we modified the physics course to try and do that. And we're still in the process of perfecting this, but we've got some pretty good preliminary results that this works. Okay, let me now sort of go into some really more detailed things about the research in really science education in general, but as physics specifically, on the specific things that you can use in teaching practices. And so this is kind of my attempt to capture an overview of all the research, what it tells us about what's important for supporting student learning. And so the key part, it's sort of at the center here, is the learning where they need to practice the thinking, solving problems, etc., that you want them to learn with good feedback. And the feedback that they receive needs to be particularly effective to support learning, needs to be timely, specific, and actionable, so they know what to improve. So that's really the heart of this. But then there's a lot of research that goes into what's important for designing the practice tasks that they're going to be working on, and how to best implement them in the actual classroom setting. But I'll just put in passing that I think this body of research really defines teaching expertise in a way you couldn't have done 10 or 20 years ago, in that it really shows the specific practices that research shows that if a teacher knows about and uses them, they can produce more learning. So let me go through, I don't have time to go in detail through all of this, but I'm going to go through some of these more specifically. So in terms of what goes into designing the practice task, first, you want the disciplinary expertise, the way of thinking and the knowledge of the discipline that's relevant to the learning. And so in terms of what goes into that, I'm going to refer to a big part of that, I think, has come out of some research my own group has been focused on the last few years, looking at how experts in a variety of different areas of science and engineering solve authentic problems in their field. And this includes a number of physicists. And we found that the problem-solving process, which is really at the heart of expertise in science, their problem-solving process was defined by making a particular set of decisions with limited information. And the thing that was most striking and surprising to us was this was first a fairly finite number, 29, but more striking was the same 29 decisions were used almost all universally, consistently across all these different experts in the different disciplines. Now, that probably sounds kind of hard to believe until you start looking at the nature of what these decisions are. There are things like the expert encounters a problem, they have to think about what concepts and mental models are relevant to solving it. They have to decide what information they need to solve it and what isn't relevant, and how to find that information. They need to decide what approximations and simplifications are appropriate, and so on through the list. And so you can see that set of decisions is something that it's easy to believe that a whole variety of different problems in science, you'd still have to make those same set of decisions. Now, I want to emphasize, although the decisions themselves are generic, they apply in many different contexts. Actually making the decisions, that always requires specialized knowledge in the discipline, and that we see the experts really have their knowledge in their subjects organized around making the decisions, so that when they're faced with a decision, they recognize what knowledge to use and how to apply it. And so what this tells us is sort of to develop, physicist expert thinking, you really want to have these practice tasks, having the learners practicing making these problem-solving decisions in some authentic problem context. And then they have to use and practicing using the knowledge and reasoning of experts to do that. So, because I think that it's so important that people recognize the need and what these problem-solving decisions are, and have the students actually being explicitly practicing, I'm just going to give you a minute to read through the list that we've identified here. And as you're reading through, you might think about what are the most important and which you might think might be the most difficult for students to learn. So I'm just going to stop talking here for a minute and let you read this. Okay, so now when I am there with an audience, I'll often get people to volunteer which they think are the most important and most difficult, or particularly most important. And what I always get is a whole range of different answers. And this sort of emphasizes the point that I like to make, which is that really all of these are at some level essential to good problem solving process. And so one really needs to have opportunities for students to learn all of them. But the problem is that if you look at the typical physics course and the typical problems given in the course in exams, you find, and we've done this analysis for a number of different physics courses, that nearly all of these decisions are actually removed from the typical course problems. And so that there's students who are actually making a very small subset of these decisions as they're going through the normal problem. And one of the results of this is that students are learning information, but really not how to use that information to solve authentic problems. And if you think back to where I talked about the problem with with the graduate students coming into my lab, not knowing how to do physics. This is largely at the heart of that deficiency that I saw in them. And you might ask, what is it about the problems that really make having so few decisions? And so there's certain things that are often done that sort of remove the decisions that students need to practice. And so one of them is providing all the information that's needed and only the information that's required to solve the problem, telling what assumptions to make or what to neglect. And it's possible to solve many of the problems just by plugging in to an equation or procedure from that week. So the student doesn't really have to decide what concepts are important. They know from the way the problem is given. They only call for one representation and never ask why an answer is reasonable or justified decisions made in the problem solving process. And so these are all very standard practices for your standard physics problem, but what it means is the students never get the practice they need to make decisions to solve real physics problems that you want them to be able to do later. But we've also seen it's quite easy to make small modifications of the standard problem to actually bring in numerous more decisions. Okay, so moving on here to the other features, I think, yeah, so I'm just going to briefly touch on prior knowledge and experience and motivation. These are important, but I think they're pretty familiar to most everybody, so I won't spend much time on them. The key thing is you need to connect with and build on the student's prior knowledge and experience. And one of the challenges that varies with different students. And so it's hard to be perfect for all the students in your class, but you always have to do better. But the key aspect here is to find what's a suitable level of challenge, because what's been shown that's most effective is to have tasks that are very challenging for the learner, but not impossible. So they can succeed, but they have only if they put in intense effort. But making that right level of challenge depends on where their starting point, they're starting from. And so you just have to try and make that right. And then motivation, and the motivation to learning is really shown to be a critical element. And there's this is, again, something varies a lot with student background. But one thing we do know that enhances motivation is to put the material in some context that the student can see as reasonable, is interesting and meaningful. And another important feature to motivation is to have the student really believes that they can learn the material and they know how to learn it, and that so they can get a sense of accomplishment as they progress through and learn more. Okay, but that's just very quick overview of those things. I want to say more about the brain constraints, because these are some really quite important elements of learning that are almost unknown for most physics faculty. And the most important one is the way the memory works. And so you can model the memory as really having two components. There's what the second component is the long-term memory. And this is what most of us, when we refer to memory, most of us are thinking about. It has, this very large capacity. You can remember an enormous number of things, and it operates over long duration, years, decades, etc. But then what cognitive psychologists have shown is that there's also a second component, the what they call the short-term working memory. And this is like a buffer that information and ideas have to go through, and they go into the short-term working memory, and then before they can be processed and move into the long-term memory. And this short-term memory is very different from long-term in that first, it has a tiny capacity. This is typical human brain, somewhere in the range of 5 to 7 items. And it operates on time scales of minutes that it can retain over. And it's really kind of it's the amount of things your brain can pay attention to at the same time. And so this is really critical because of this limited capacity, when the brain sees or hears new items, some new thing it's paying attention to, it pushes out old things out of this working memory. And so they get often pushed out before they can be processed and get into long-term memory. And so this has tremendous implications for teaching, because it means that if you add more elements that the brain's trying to keep track of, it just pushes things out and reduces the amount of processing and learning the brain can do. And so there's a number of things that can happen in the classroom that cause this problem and really hurt learning. And probably the most serious one is the split attention, where maybe the students are looking at their mobile phones or checking email and something, and basically doing that, they're taking up a tremendous amount of their working memory. And so it really is a disaster for them actually paying attention to and learning the main material in the course you want to have. But there's also a lot of things instructors can do that put unnecessary load on the working memory, like introducing jargon that students aren't familiar with. Even if you define what it means, anytime the student has to think about it, it's something new and it takes up working memory. Just introducing way too many topics overwhelms working memory. And even some other things like making a fancier picture to illustrate something that just makes it look nicer, but has additional features that make it more attractive, but capture students' attention, or even little interesting digressions or jokes. These actually hurt learning because they take up attention away from the main learning that you want them to have. And as I say, the brain has this stringent limit, and so any additional attention on something else actually reduces the effectiveness. Okay, let me move on to say a little bit about data research on implementation in the classroom of these kinds of activities. So I talked about designing good practice tasks as above, but we've also seen that it's important that there be clear deliverables, things the students has to actually complete as part of their task to define the task and then make it more useful for the instructor to give feedback on it. And then there's the second and probably more important is the idea of social learning. And it turns out the benefit of students working in small groups, and optimum is something like 3 to 4 students in a class. And oftentimes faculty who are not familiar with the research on this can be quite surprised and have trouble believing that there's benefits to having students talk to each other more than just listening to them, the instructor, the expert, explain the topic to them. How can this actually be better? But in fact, it really is, and we have some good data on that. And there's a couple of reasons for that. One is the students can get more individualized feedback from the other members of their group. The student will be able to address exactly what confusion they have, where an instructor explaining the topic in general won't be able to do that. But then there's another probably more important process, which is the brain has a lot of elements devoted to social interaction. And so it's been well studied that if people are teaching something or just explaining something to someone else, or even just thinking about doing that, it actually brings in some unique cognitive processing that the brain saves for social kind of interactions. And that additional cognitive processing actually produces learning more so than having this when the student is just studying the material on their own. So there's a kind of fundamental additional mental processing value in having students talk to each other. Okay, so I'm going to finish up here and leave time for questions. So the conclusion I want to say is that we have lots of research now showing what's good teaching design and implementation for it, and good data showing that it leads to better learning than the traditional lecture approach, and we understand why. But before I get into other questions, I'm going to pose my own question that I often get after this talk in one version or another, where the faculty members will say, well, traditional lectures can't be that bad because we, as university professors, we were taught that way by traditional lectures. And my response to that is, really, that's exactly the same reasoning that was used to justify bloodletting as the medical treatment of choice for actually 2,000 years. And it really only was possible to go beyond that when we start recognizing the importance of doing real science, which in medicine meant having proper comparison groups. And so you can't really say that a treatment is effective because the body itself has set up to get better, and it's also set up to learn. And so it's really only when you can do careful comparisons like we're talking about that allows you to really know which is more effective. So with that, I'll finish. Here's my conclusions. If you want to learn more about some of these things, here are some books that are some of my favorite references on the subject, and a couple of articles that might be useful. And I'll make sure that my slides are available because I've probably covered more things than you could keep track of in your working memory. Thank you for your attention.
Thank you very much, sir. Professor Ahluwalia, sir, kindly unmute yourself. We are not able to hear you.
So thank you very much, Professor Carl, and we enjoyed your master class. That was wonderful. And, I would request our participants here to ask questions, and they can post their questions in the chat box also. But let me begin with the one question which was coming to my mind. And that was that you very interestingly made one very crisp two-word remark, and that was framing authentic problems. I mean, that is something striking to my mind, that how does really we let the teachers develop that kind of a thinking, the implementation of the 29-point plan, I believe. So that's very crucial. How we can go about that, I think IAPT can really work in that direction very critically, because that's the most interesting part, which I feel is learnable and implementable also.
Yes. So the I mean, what I'd argue is that first one needs to pick when I say an authentic problem, it's really, so oftentimes we have problems in physics that are grossly oversimplified and nobody would care about except a physics professor, with pulleys and masses or masses on frictionless inclined planes. And so part of the problem is to first kind of think about a more realistic real world problem. Those are almost always come with more decisions going to be involved, and it's not easy, but it's also not impossible to usually think of the physics material you want to cover and then think about some more realistic real world situation where that would apply. But then you also, what you can do is when you're having the students put a solution to the problem, rather than the solution being just give some number, and that's the final answer, you can actually have them their solution could be having to make specific decisions and justify these problem solving decisions as part of their solution process that they're going to turn in and get evaluated on. And now, you need to give some thought to that, because obviously you don't want, or not all of these decisions are relevant to every level class. And so you kind of need to look at what level course yours is and what are the specific decisions that you think are most important for students to learn at that level. So in our beginning introductory physics class, we picked out 10 of those that we think, okay, these are particularly meaningful and going to apply to every student, even in introductory physics, that we have students go through. The other point I should make is, when you're trying to think of what a good authentic problem is, you need to think about the problem needs to require the particular physics knowledge and particular physics topics you want the students to learn. That needs to be used to solve that problem, so that they're learning the material as a way of solving problems, and because that sort of has the material then best organized in their brain sort of for future use.
So that means that problem also becomes a vehicle for delivery of the content also.
That's exactly right. Yes. And I think, and I think that is a particularly important aspect of making sort of knowledge as it needs to be used to be learned that way is more effective.
Thank you. Now we have some hands raised, Professor Pal. Let me invite Professor Kulkarni. He has raised his hand. Please unmute yourself and ask the question, Professor Kulkarni.
Yeah, I have one observation which I thought was very important. Professor Wieman was kind enough to reach the neurological basis of teaching and learning, which means that the teacher has to turn his or her attention to what is happening at the brain level when he or she teaches, and also what is happening at the brain level when the student receives the teaching that has been done. So pushing the whole problem to the neurological environment is something that attracted me, and I was thinking about it for the last 4 or 5 months. In fact, we had conducted a meeting only on 2 days ago on a different topic of a neurological basis of learning. That's what. Second thing is, I was also curious to know what exactly is the role of demonstration of physics experiments as far as the learning is concerned. I am sure that it has some basis, but the what takes the cake is the demonstration part or the thinking that sets in when the demonstration happens. My attention is more than the demonstration, how the demonstration gets received by the learner and how correctly the demonstration is done by the teacher. So this is my basic question and an observation. Thank you.
Yes, so I think the neurological part is self-evident. The demonstration, so there's been some research on physics demonstrations, and there's a couple of things that are quite interesting in this. One is that they often aren't very effective in normally given. And the one most striking result is many physics demonstrations are made to give kind of unexpected, surprising results to get students' attention. But when people have tested this, what they found is in many cases, later on, what the students remember is not what the demonstration actually showed, but what they were expecting it to show. So it's actually very counterproductive. But that doesn't mean in demonstrations have to be ineffective. There's things that people have found that are important for making it effective. One is first to make sure that students understand how the equipment works and what the demonstration is really involved, and in that's often sort of too neglected, and the students don't know, they're not focused on the right things because they don't realize what's important and what isn't important, and so everything is kind of confusing and overwhelming to them. So there needs to be very clear sort of what the demonstration's doing, what the different parts of the equipment are that it's being used. But then it's also, it seems to be very important that the students have to make, before the demonstration happens, the students have to make explicit predictions of what they think is going to happen. And then after the demonstration is carried out, they then have to have a follow-up examination on what they predicted versus what happened and why. And so it involves a fairly extensive sort of activity based around the demonstration that really gets the students much more deeply thinking about what's happening rather than it just being something to catch their attention. But when you do this right with the more extensive things, then demonstrations can be quite effective. But just doing it to show something quickly and unexpected turns out to not be very effective.
Okay.
Thank you.
Now we have Professor Mashood.
I'm in.
Basically in Homi Bhabha Center for Science Education and Research at Mumbai, and he is a practitioner of physics education research. He has done his PhD in PER itself. Yes, Dr. Mashood, please ask a question.
Thank you, Professor Ahluwalia. Thank you, Professor Wieman, for the insightful talk. So my question is regarding that pre-final slide. That pre-final slide where you said traditional lectures, many traditional instructors have this impression that what they do works. So regarding that, there is the work from your colleague Daniel Schwartz and the paper titled Time for Telling, which says that lectures or telling works if the student is sufficiently prepared. So is it possible that in a class of say 100 students, there may be 4 or 5 students who are prepared, and can this be the reasons why traditional lectures have this perceptions that what they are doing is working? What's your comment on that?
Yeah, so that's a good question. What I would say in Dan's work on a time for telling, and I interact a lot with Dan and discuss it. So, I think you're absolutely right that people can learn from being told something, but they have to be prepared to learn from it. And so where I sort of stress, in the way I'm talking about teaching, the instructors, I keep talking about giving feedback. Well, that's, that feedback is in the form of lecturing to the students, but because the students have struggled with the problem first, they're really much better prepared to learn from it. And you can think about that telling as just the feedback that they're, getting on their thinking. Now, in terms of your other point about some students may be already kind of prepared in their thinking to learn from it, I think that's probably right. I don't know of any great research on that, but whenever we do particular studies of measuring what's learned from lectures, we see on the average very little, but there are always a few students who seem to score pretty well. And so I think that's a lot has to do with their backgrounds and their thinking ahead of time, that yes, some can be successful, but many more would be successful if when went to more research-based learning.
Absolutely, yes. Thank you.
So thank you very much. So there is another hand raised. Kaushik Das, please, Dr. Kaushik, ask a question.
Kaushik Das, please unmute yourself first.
Oh, thank you. So thank you, Carl, for this fascinating talk, as always. And my question is, just by posing these critical thinking questions in class and asking the students to reflect on it and maybe make a mistake and learn from there, would that be that memory go into long-term memory without doing a follow-up hands-on activity, or it will just remain in the short term and go away afterwards?
That sort of goes to my previous point about, that's going to depend some on the students. There's some students who can be very actively processing something, even with sort of a simple immediate question. They'll think about it a lot more. But the great majority, I think, really need some more extensive follow-up and guide, structured processing of the ideas before it will go into long-term memory. So I think in general, almost always it needs something more than just asking the students to think briefly about something. They really have to do more processing, some sort of more activity that they do, more deliverables to really get the extent of mental processing required for it to be retained.
So the activity can be just a mental activity or the role of hands-on activity. What do you prefer?
Well, when you say mental, I mean, I writing out a solution, for example, or presenting it, explaining something to somebody else, presenting it. I think those can all be just fine. And I would say, if by hands-on some kind of experimental thing, I'd say that's certainly not necessary. That it's really the mental processing that's required, and sometimes that can involve hands-on activities, but many times it doesn't, and it doesn't have to.
Okay, thank you. Now we have Anshumala Gupta. Anshumala, please ask your question. Unmute yourself. Yeah. Start your video also.
Can you hear me?
Yeah, we can.
Yeah. Thank you so much. Professor, I work with a large number of teachers across India, and most of them are graduates and postgraduate. And the major problem I'm finding with them is not having shared meanings of conceptual words. I say something, or okay, the facilitator is saying something, and what the other side is hearing, the meaning is not identical. Even meaning to words like force and energy and momentum. I mean, people actually even confuse between terms like force and energy. I mean, and it doesn't matter what level they are teaching. That's not really the problem. The problem is conceptual words which hide a full-fledged theory, and which hide a large number of connections and meanings behind them. When they are said in a lecture or otherwise in any discussion also, if that meaning is not properly shared, almost nothing is transmitted. So do you have a solution?
I think from the perspective of kind of establishing meaning of terminology, there one can really probably fall back on language learning. And what's important for language learning is really to use the term and use it in discussions, and have to call on it repeatedly. And so that doesn't automatically mean that they have the correct meaning for it, but it through that process it helps develop and sort of more establish their thinking about what the meaning is. And so this is sort of another note about the value of having students work together and talking about things, is that actually helps them master the technical terminology much better too, if they are in discussions where they're needing to actually use it repeatedly.
So, okay, thank you. So Anshumala, I hope you got an answer to your question.
I don't think I really completely answered it, because she's raising some just learning challenges that a lot of people don't understand these things, and I can't give you a simple way to fix that, I'm afraid.
We have another hand raised. Professor Sivakumar, please ask your question. Unmute yourself.
Yeah, Professor Carl Wieman. I hope you remember I'm organizing a physics training and talent search program. You helped us once in 2021 to organize an online workshop with two of your colleagues. They were resource persons, to recall. You have helped us in that. Yeah. See, the sort of a question is, you see, there's a Daniel Kahneman recently who died, economic Nobel Prize winner. He has some short-term, quick decisions and fast decisions. You have a short-term and long-term memory. Are these two sort of concepts related to each other in the pedagogy? That the decision-making in the larger system is used with the concept you introduced also sort of appears to be somewhat similar.
I'm not sure. I missed a little bit of the early part of your discussion, so I didn't completely get the question. Can you repeat? Yeah.
I mean, see, there were some discussions on thinking by Daniel Kahneman. I think he is an economics Nobel Prize winner.
Yes.
He has a quick decisions and fast decisions and all. And you also have a quick learning, a quick term and short term, and these two. So I was just asking, those two have any similarity or relationship?
Yeah. So what I'm familiar with Kahneman's work, and what I think is this kind of type 1 and type 2 thinking. And I think that almost all of what we're doing in physics education is trying to get students to do type 2 thinking. That, that's really the type 1 is kind of the quick, simple, simplistic results. And really any kind of serious scientific reasoning or problem solving, you really need the deliberate, the the more challenging type 2 thinking. And so, you know, I think when we look at students' misconceptions about simple ideas like do heavier things fall faster than lighter things, those are things where their first response is sort of type 1 simplistic thinking, and so you're just trying to get them conditioned that they have to be more thoughtful, more careful, and invoke type 2 thinking. So, but almost, I'd argue that virtually everything that we want them to learn is type 2 thinking. So.
Thank you very much. I think now there are no more hands raised, but there are questions in the chat. I will read one by one and maybe you can respond. One is, how do you see the future of quantum computing in terms of physics teaching?
I don't think I had prepared to give a adequate answer of that. I mean, I taught quantum mechanics, and the quantum computing fundamentally involves entanglement, and entanglement's just a very challenging concept. And so I think clearly we're going to have to find a way to put it into physics teaching, because it does seem it's getting increasingly important, but how to do it, I don't know. And I think the other question really is how much people really need to understand the deep physics of quantum computing, the deep quantum mechanics, to actually use it. I mean, I think almost very few people actually understand the physics of integrated circuits, but they can happily use them and apply them in many cases. And so I wouldn't be surprised if quantum computing is similar to that.
Okay, thank you. And another question is, how important are hands-on activities in the learning process?
So I've actually done research on the significance of where people had instructional labs that accompanied courses. And we found that these instructional labs carrying out experiments to sort of demonstrate the concepts had zero impact on the learning. It was very striking and so, I'm convinced that it's not that they can't possibly be useful, but that they are not nearly as useful and meaningful as is assumed. And that, the really critical is what I would say is minds-on. It's the mental processing that one does, and how involved the hands are is pretty irrelevant, really, I would say.
You have made a very, very interesting comment on this, that minds-on is very crucial.
I mean, the other thing is I didn't talk very much about technology, but the real value of technology is when you use it to support the mental processing that you think is important. And we have some good data showing that PhET simulations are, for example, better than actual real experimental apparatus for having students actually develop the conceptual models and so on. And just because they sort of more directly support and help the thinking that for the students to develop. So, but that is an interactive activity where they're changing things and seeing what results from it, and learning from that process. But it's on a computer screen, not in an equipment.
Thank you. The next question is very important, Carl, because in our national education policy, they are emphasizing now that we should have 4-year undergraduate degree, but the 4th year must be devoted to research. And the question which Dr. Sanjay is asking is this: please throw some light on my question, how we can provide holistic research temperament in undergraduate level students.
So that's a very good question. And I can really only speculate on it. I mean, I find that there's tremendous educational value in having students be involved in research. And in large part, I think it goes back to the decision making. I mean, one of the things we've looked at is students getting involved in undergraduate research. They're making many, many more of those problem-solving decisions than they ever get in their classroom experience. And so that just shows that I think kind of why it's a great educational value. How to make it happen most effectively, and how to train students for it is then a more complicated issue. And, again, my main, without any data, my speculation would be that it really involves thinking about the decisions and the fact that the students will be in research, will be having to make many more decisions, and that the most effective research experience is one in which they have practice and feedback on making a whole variety of the authentic problem-solving decisions in a research context.
Yeah, thank you. I think
now how to do that at scale for many students at once is then a whole different and big challenge in how to figure that out that I can't answer.
Yeah, thank you. This was a similar question by Dr. Mashood also. I think you have answered this very nicely. Then there is another question which is by Kari. Is there any period or number of times repeated practices that leads from the short-term memory to the long-term memory?
You're saying, is there a number of
is there any time period or number of times repeated practices that leads from the short-term memory to the long-term memory?
Okay, yeah. So there's different ways to answer that. So it's not so much the time, it's the type. And so, for example, they see that really deep processing of the material. So, for example, testing yourself on it is much more effective than just kind of, for example, rereading it or rereading something. And so the type is important. There's a lot of research just on long-term memory and how to enhance that, which is a little bit different, but they've shown that sort of spaced repeated, so processing that's spaced out in time, where it sort of starts from short time intervals and then the time interval is increased, where you're going back and reprocessing, testing yourself on it, thinking through the ideas again. It just doing that repeatedly and at longer and longer time intervals leads to greater and greater, very long-term retention.
Thank you. And then there is one very important question, but that's the last question. And that is, do you expect AI apps coming in near future which will be most useful to teachers to teach physics more efficiently? I would rather add to it, most useful to the learners to learn physics, not only for teachers to teach physics, but for learners to learn physics. These AI apps, artificial intelligence apps.
So you're asking, so your sound cut out a little bit at the beginning. You're asking, what do
The
I think about
influence,
using
influence of artificial intelligence applications on teaching learning processes?
Yeah, okay. So yes, how artificial intelligence comes into this, that's a big question lots of people are worrying about. And, you know, I don't know the answers. I can just tell you a little bit about what we've been doing in my own group and some others I know well. I mean, there seems like there's a significant potential to have artificial intelligence, these large language models, be sort of individual tutors for students that could give them kind of individualized feedback at the level that helps them. That would be very valuable, but it's pretty challenging to have them do that right now. What we've found and others have found is that these models are really, it's sort of as a fundamental part of their design are to give answers. And so when they're supposed to be kind of as a good tutor doesn't give answers, they sort of they give questions to nudge the students into developing their own understanding. And so these tutors very often just kind of give answers, and so that's a problem that we and others are struggling with. I have seen some work out of Harvard. Kelly Miller has done it, where they have actually done experiments where they were quite hard to program the artificial intelligence on particular problems, and they got very good results, that the students learned substantially more from that than they did in good classroom activities. So I think there's clearly potential, but we're a ways away from making it work. And that's almost all the work I've seen is people sort of setting things up, but they don't really have data on how effective they are with students yet. And there are some basic challenges with how to do it. And the other thing we've seen is that on the artificial intelligence, it does pretty well at solving and therefore being able to help students on sort of the quite simplistic artificial textbook problems. But as soon as you give it a more realistic problem that involves some kind of real world knowledge and thinking, then they're very poor at that. So that's the other big limitation that we're seeing now. But I'll just leave it with one final comment about artificial intelligence, though, that's completely aside from how they can be used in teaching. And there's a much more basic question that I struggle with, which is that what it's going to mean to be an educated person in the world of artificial intelligence, where so much of what we are teaching students how to do, they can just get the AI to do for them. And so, what it really means, what you really want education to be in that case. And I think it's very much an open question right now, although I would argue probably these kind of general problem-solving decisions where you have limited information that you sort of have to make just a good educated guess is probably the place where humans are still going to be valuable for a long time.
Thank you. There is one final question. Vandana Luthra, ma'am, please ask your question. Unmute yourself and ask your question.
Good evening, Professor Karl, for your insightful talk. And you mentioned about the short-term and the long-term retainment of the memory. Each student is endowed with a unique set of learning or memory, which can be modified with the practices. But is there any standard method which can be used in the classroom in order to map that how much memory a short-term or long-term a student has, and so that his or her lessons can be adapted or can be tailor-made for pedagogical purposes?
So I think first what's relevant here is the short-term memory, not long-term. I mean, I think everybody's long-term memory is very large and has a very large capacity. And so that's, I mean, aside from people with learning disabilities and so on, but there is variation in short-term memory, which is kind of then more immediately relevant. And there are measures of short-term memory capacity, and it does show some variation, and that variation certainly affects learning, but I'm not sure it's particularly relevant for the classroom design, because in what we know from research is that anything that sort of adds unnecessary, what we call cognitive load, unnecessary demands on the short-term memory always inhibits learning, and that's sort of independent of every student. And if they have a smaller short-term capacity and short-term memory, it might make more of a limitation to them, but the variations aren't great. And so I think really it's the optimization is really, you just want to think about for everyone, reducing the unnecessary cognitive load is going to be more beneficial, and you don't really have to try and separate out one student from another in that regard.
Okay. Thank you so much. Thank you.
So thank you very much, Professor Karl. And I think it has been a wonderful session. I just want to thank you for another thing, Professor Karl, and that is the kind of investment which you made of your Nobel Prize award in making that a reality. I think we are thankful to you for that, because we have already seen and used the results of that which you really contributed. I think that's great and amazing contribution which you have made in terms of spreading knowledge apart from your winning of the Nobel Prize for a great discovery. I think this is a very interesting social responsibility which you really have carried forward to make this a reality, that we are able to use these facilities sitting in the remotest corner of the world. Thank you very much for that. On behalf of IAPT, once again, I thank you for your wonderful lecture. And I think we need to really listen to this maybe in some study sittings, so that we can fully carry forward the ideas which you have put before us. Thank you very much. Sapna, please take over.
Yes. So thank you very much, Professor Karl Wieman. We are grateful to you. So on behalf of IAPT and all the colleagues who are sitting here, I extend a big thank to you. And you have actually shown us how we can remind us how that the heart of education lies not just the transfer of knowledge, but the profound and noble task of igniting curiosity, fostering critical thinking, and nurturing the next generation of scientists and thinkers. So we are eternally very much grateful to you for sparing your time and being with us. And once again, thank you very much. Have a good day. And thank you very much, Professor Ahluwalia, for chairing this session. So good night, everybody, for patiently listening to this beautiful talk. So I think we'll meet again. Professor Karl Wieman will meet again in another beautiful talk and sharing knowledge with us. Thank you very much, all. Thank you.
It's been a pleasure. Thank you.
And namaste from India. So thank you.
Thank you. Thank you, sir. Can we end the meeting?
Thank you, sir.